Okay. I think the most important thing to do at this time is for me to express my view that this has been a splendid conference, and I am extremely grateful to Detlef for the wonderful job he did in putting this together, and to Philippe as well. Now, what I'm about to do, well, let me say this. I think that Travis's talk was really a perfect final concluding talk for this conference. So this, I wouldn't want to say what I'm about to do is give a talk. Probably it's just a chaotic collection of comments on what has transpired here, or what the things I find perhaps fit together in some sort of coherent whole. So my first comment is going to be about the title, Quantum Theory Without Observers. I think all of you have heard enough about what that means to have some sense of why one would want to have a quantum theory without observers. But I would like to begin with a fairly modest statement of what's wrong when you don't demand quantum theory be a quantum theory without observers. So this quote: in the post-1925 quantum theory, the anarchist position became dominant, and modern quantum physics, in its Copenhagen interpretation, became one of the main standard bearers of philosophical obscurantism. In the new theory, Bohr's notorious complementarity principle enthroned weak inconsistency as a basic ultimate feature of nature, and merged subjectivist positivism and anti-logical dialectic, and even ordinary language philosophy into one unholy alliance. After 1925, Bohr and his associates introduced a new and unprecedented lowering of critical standards for scientific theories. This led to a defeat of reason within modern physics and to an anarchist cult of incomprehensible chaos. A modest statement. Let me read this quote from Bell, which I'm not sure whether Travis had this or not. We had so many, but I do have a few more. A final moral concerns terminology. Why did such serious people take so seriously axioms which now seem so arbitrary? I suspect that they were misled by the pernicious misuse of the word measurement in contemporary theory. This word very strongly suggests the ascertaining of some pre-existing property of some thing, any instrument involved playing a purely passive role. Quantum experiments are just not like that, as we learned especially from Bohr. The results have to be regarded as the joint product of system and apparatus, the complete experimental setup. But the misuse of the word measurement makes it easy to forget this, and then to expect that the results of measurements should obey some simple logic in which the apparatus is not mentioned. The resulting difficulties soon show that any such logic is not ordinary logic. It is my impression that the whole vast subject of quantum logic has arisen in this way from the misuse of a word. I am convinced that the word measurement has now been so abused that the field would be significantly advanced by banning its use altogether in favor, for example, of the word experiment. I would think that would be a suggestion which might be particularly appealing for instrumentalists and operationalists who presumably must be regarding what they're doing as not measuring some non-operational thing. But what I really want to comment on here is relate this quote to some of the things in Jörg's talk, particularly the violation of the sum rule and the violation of conditional probabilities, which I think you mentioned. And the only point I want to make about that is that Jörg, is when you first introduced those probability formulas at the beginning of your talk, those were formulas for probabilities for results of experiments, certain experiments. As such, there was nothing problematical or surprising about the sum rules being violated, because it would make, well, I think in the simplest case you consider a sequence of 3 experiments, and you have a joint probability for the distribution of the 3 results. And then you point out the violation of the sum rule is if you sum over the probabilities for the intermediate result, you get a different joint probability distribution for the remaining 2 from what you would have had if you had ignored the middle experiment entirely. That's perfectly reasonable since if the middle experiment is relevant. And similar comment would apply to the formula for conditional probabilities. There's no problem with the conditional probabilities if the conditional probabilities are simply probabilities, conditional probabilities for what would happen in a certain experiment. Things become strange if you regard those probabilities as probabilities for what was there independent of whether you looked. And of course, the rest of Jörg's talk was an attempt to arrive at an understanding of those probabilities for a suitable set of observables for which you can regard those probabilities as describing what was there independent of looking. But I'll come back to that later. Now, just an initial comment about consistent histories. What has always bothered me about the typical formulations of consistent histories is this. Well, many things bothered me about it, but one thing which is particularly striking is that this theory, as it's generally presented, gives you a collection of probability statements which are not to be interpreted as directly about results of experiments, but about what is there regardless of whether you look. Then when you apply the formalism to situations where you do have devices, measuring devices and so on, you obtain the original results, but it's supposed to be something which makes sense regardless of whether or not you look. Consistent histories is intended to be a quantum theory without observers. And the problem is that when you take this totality of probability formulas together, you realize that they can't all be true. They're inconsistent. And the way this is argued, again, avoided, let me say, I don't know what's the right word to use at this point, Tim? Attempted reconciliation is what? Swept under, excellent. The way this is swept under the rug is by saying, invoking something which was once called Rule 4, it's expressed different ways. It's the insistence that in this kind of theory there's an additional rule which says you're not allowed to talk about these different families of probability distributions, which would, if you did talk about them and analyze them, you would see they are incompatible. So there's a rule you're not allowed to talk about them at the same time. Now, whether you have this rule or not, they're still incompatible. If you're not allowed to talk about them, then maybe you're not going to be able to talk about the incompatibility, but the incompatibility is not changed by rules about what you're allowed to say. Now, one of the reasons I would say this is a case where the cure is worse than the disease. The disease was Copenhagen quantum mechanics, for which there are no inconsistencies. There is only the implausibility that Copenhagen quantum mechanics understood instrumentally about governing results of experiments. And it's a perfectly consistent set of rules which physicists use all the time to make predictions. And many of us here, of course, and that's why we're having this conference, are not satisfied with such a set of rules as providing us with a fundamental physical theory, however useful that set of rules may be. So what has happened in some cases is people have come up with alternatives which are just blatantly inconsistent. This would seem to be a perfect example where the cure is worse than the disease. I will come back to consistent histories later, because what I find one of the most satisfying developments here is that the formulations of consistent histories which were arrived at here are formulations which avoid that problem.
I think that probably you can make everything okay if you say that you limit the families of...
Absolutely right, and that's why, absolutely
and in fact,
right.
this was suggested by Gelman sometimes.
That's absolutely right. So Giancarlo was saying, and I'm going to come back to that later, if you limit the families that you talk about, and Pierre referred to such possibilities at the end of his talk, if you limit the families so that you don't have together families which are inconsistent, you get to avoid the problem. But what I insist on is that most of the papers on this subject, that is not the route taken. The route taken is invocation of Rule 4. You're not allowed to talk about them. You don't select a family. You just say you're not allowed to talk about them altogether. That's an instance of the cure is worse than the disease. Griffiths was particularly insistent on that. Gelman and Hartle, the way they talk, would suggest thinking about maybe doing some limiting, maybe for different reasons, but certainly not as dogmatic on this point as Griffiths was. Absolutely right. Here's another Bell quote. I'm not sure whether Travis had this one, did you? In physics, the only observations we must consider are position observations, if only the positions of instrument pointers. It is a great merit of the de Broglie-Bohm picture to force us to consider this fact. If you make axioms, rather than definitions and theorems, about the measurement of anything else, then you commit redundancy and risk inconsistency. Yes, Jörg.
And that is that you only measure basically frequencies of light signals.
Whatever what you call measuring of frequencies of light signals is ultimately going to be recorded in ink marks on paper.
No, but in my eye, you know, all I measure are.
We can talk about that later. The point I want to make here about this quote is, so Bell is here responding to the criticism that in Bohmian mechanics, you only positions, this is a theory limited to positions. All the other quantum observables are simply not included in the game. The statement he's making here is that insofar is more than a statement you don't really need the other observables because you can handle results of measurements if you have just position variables, if only the position of instrument pointers. But he's saying more than that. Is a danger of having axioms about other observables because these axioms about what would happen by other observables would have to either be consistent or inconsistent with the rules you already have for positions, that position alone should be sufficient, and there's a danger of saying more. Let me go a step further by saying, look, suppose you had a particle ontology, and suppose you have in this, and suppose you within this ontology, you've got the world lines of an n-particle universe. The first thing you would like to say about that situation is whatever other properties you want to associate with these particles should be properties of the world lines of these particles. You shouldn't need them as somehow free-floating properties having nothing to do, not definable in terms of these, what you have already, the trajectories of the particles. You might say, well, look, I still would like to have these extra properties, these free-floating properties, and of course, you're free to do so, but you should not do so just because we talk about these things in quantum mechanics. You should have a good reason for doing so. What would be a good reason for doing so? A good reason for doing so would be if, in fact, adding additional properties provides a simpler, more efficient description than the one you had without adding these properties. Just like the addition of the electromagnetic field, electrodynamics provides you a simpler theory. You should not introduce properties just for the sake of introducing properties or because we're seduced by language to think there's got to be a property. You should have a good reason for introducing them. Is there a question?
I think what you may be risking inconsistency, but I think this community is a bit afraid of risking to do any physics. So if you look at Harald Weinfurter's talk, which was a very competent description of how you could build a source of the type you wanted, there was not a word about position observables. They were totally uninteresting to the project he had. Now, resolving that all into position would just be sterile and uninteresting. So I think there is a risk maybe in doing physics, but I think it would be also interesting to take that risk.
I'm not sure I understand the point. I mean, my reaction to those experiments in Bohmian mechanics would be that Bohmian mechanics may not be terribly illuminating with regard to those experiments, but they're still interesting quantum experiments and interesting tests of quantum theory. I don't see why, since you operationalists aren't taking any particular realist view about position anyway, you're taking the same view about those observables as a Bohmian would. That's why I don't see why there should be any disagreement with us on that point. Bohmians are not realists about every property, everything that's called a property in quantum mechanics. You are a realist, presumably, about even less. One should not be a realist about more than is reasonable to be a realist about. I think Travis had part of this quote, but he left out my favorite part. So I want to read it. This is another Bell quote. It is important to note that to the limited degree to which determinism, hidden variables, pre-existing values, as Travis explained, it is important to note that to the limited degree to which determinism plays a role in the EPR argument, it is not assumed but inferred. What is held sacred is the principle of local causality or no action at a distance. It is remarkably difficult to get this point across, that determinism is not a presupposition of the analysis. Despite my insistence that the determinism was inferred rather than assumed, you might still suspect somehow that it is a preoccupation with determinism that creates the problem. Note well, then, that the following argument makes no mention whatever of determinism. Finally, you might suspect that the very notion of particle and particle orbit has somehow led us astray. So the following argument will not mention particles, nor indeed fields, nor any other particular picture of what goes on at the microscopic level, nor will it involve any use of the words quantum mechanical system, which can have an unfortunate effect on the discussion. The difficulty is not created by any such picture or any such terminology. It is created by the predictions about the correlations in the visible outputs of certain conceivable experimental setups. Okay, I think I don't want to comment about that. Enough has been said. Now, I would like to focus on what I think is a central, almost organizing issue in this conference, the issue of an ontology for a physical theory. Whether or not a standard quantum theory has an ontology, and I would say it does. It has a sort of a macroscopic ontology. It's got to be, a physical theory has to be about something, but a quantum theory without observers can't be saying anything without an ontology. What the quantum theory about observers is about, that's what the quantum theory about observers is about. And so it becomes important to be clear about what the ontology is and to try to begin to come to grips with what would be an adequate ontology. And about that, there are many disagreements here and a variety of opinions. Here, for example, a rather general description for me is a kind of adequate ontology is what I would call a decoration of space-time. Now, by decoration, I mean a description of a kind of stuff which you specify in precise mathematics, a matter field, world lines, strings, whatever. And so to have a description which doesn't prejudice any, doesn't point to any particular kind of stuff, leaving what that ontology, the detailed ontology, is open. I call that a decoration of space-time. One could also say a certain kind of history. Decoration of space, history and decoration of space-time are fairly synonymous at this level of discussion. The histories in Bohmian mechanics, the decorations of space-time in Bohmian mechanics would be given by collections of world lines. And in GRW, it may be flashes, maybe matter density over space-time, and so on.
What about space-time itself?
And that's a good question. But space-time, I don't. It's certainly real. And if you're doing what one of the speakers yesterday did, in that theory, then the space-time itself is really treated as the ontology, because the point of the theory is to provide a dynamics for the ontology, so to speak. And in general, if you simply have a background space-time and it's not being treated dynamically, as in everything out before you get to worries about gravity and general relativity and quantum gravity, if it's a background space-time, I would call it a question for philosophers, and maybe a question of physicists, how to think about whether that space-time is ontological. It's certainly real, it's objective, and here it's just a question of language. And I don't really want to decide how to use language here. Here's a question. Can the ontology be too abstract? Maybe Tim wants to make an amendment here because he doesn't like my use of the word abstract. And so jump in, Tim, if you want. But by that I mean not involving something like local beables in more or less familiar space-time. I will give you examples. Can the ontology, something you could have, there are things which are perfectly clear as things of some kind or other, for which it is totally obscure how they could be a description of ontology, how they could provide ontology. Say what I mean. Okay, so the issue is not whether objects of very high abstraction can be a part of the ontology of a physical theory, but whether such objects can constitute the entire ontology. For example, the distinction between a pure wave function ontology, I take it that a wave function on configuration space, which is sort of the simplest kind of wave function for a many-particle system. A wave function on configuration space, I regard that as fairly abstract. It's an unusual kind of thing. It doesn't in any way correspond to a decoration of space-time because it's not on space-time. Versus a theory in which you have that same thing, a wave function, a thing at an abstract level, a very non-concrete kind of thing, and particles, as you have in Bohmian mechanics. There's no complaint there because the particle part of the ontology is what's doing a crucial part of the work in understanding how what we see around us is explained by the theory. We understand how tables and chairs and pointers end up pointing what they do when you have the particles evolving according to a dynamics which involves certain abstract entities as well. Those abstract entities don't do anything in eliminating and making it difficult to understand what the theory is saying about how particles move. And they, in fact, might afford a much more efficient description of how they move than some sort of more convoluted description which avoids their use entirely. Of course, that could be a strong argument for philosophical argument and even physical argument, still avoiding the use of rather complicated or abstract entities, but I don't have such a feeling. I don't have a problem with abstract entities, except if they're the only things in the theory. Here is sort of a hint at the idea of having a purely unusual kinds of entities, as you will see, and only those entities involved in physics at the fundamental level. This is a quote from Lee Smolin about Einstein. He says, "It is also disappointing that none of the biographers mention the writings that led John Stachel, the founding editor of the Einstein Papers Project, to speak of the other Einstein. These writings look beyond his struggles with the unified field theory to, quote, the other possibility which leads, in my opinion, to a renunciation of the space-time continuum and to a purely algebraic physics. What Einstein is saying is that the smoothness of space is an illusion, and the fundamental description of space will be in terms of algebra and not geometry. As Einstein wrote in a letter to the physicist Joachim, and okay, I'll cut to the Einstein quote in a second, but I have to say I don't find the quote quite as supportive of the view Smolin is taking than Smolin thinks it is. But let me get to the quote. Here's Einstein. An algebraic theory of physics is affected with just the inverted advantages and weaknesses of prevailing ideas, aside from the fact that no one has been able to propose a possible logical schema for such a theory. It would be especially difficult to derive something like a spatio-temporal quasi-order from such a schema. I cannot imagine how the axiomatic framework of such a physics would appear, and I don't like it when one talks about it in dark apostrophes. But I hold it entirely possible that the development will lead there. Okay, that's a very nice open-minded position, but you should take from it the idea that if you think that physics at the most fundamental level is purely algebraic, you've got a real challenge to explain how that's going to work out. Just talking about it without explaining how it's supposed to go is not very convincing. And whenever I've asked physicists, when they make these proposals, what they have in mind, what I get is, well, I have no idea, or look, I'm just talking about the language that ordinary physicists would use. They don't ask these questions. I have no idea. That's the common view. That's what I usually find them saying.
A comment here?
Yes.
I usually use that quote when I'm introducing causal sets. If you take it in context, it's perfectly consistent to think that if you see what he meant by algebraic, what he actually meant is no derivatives. I mean, there's an extension of that, which is trying to say nothing continuous.
Merely that, but then why does he find it so why does he find it then so unimaginable how it could be carried out?
Well, that's hard to say, but he obviously didn't think of a causal set as such, but he emphasizes the need for the spatio-temporal quasi-order, and that's in German the name for a partial order, which is what a causal set is.
Yeah.
So what causal sets do is they actually just say, well, we're not trying to derive it from something else, we're putting it in.
No, that's fine. Okay.
And I think he was not thinking that. My impression is that he was thinking of some theory with, say, electrons would be real, but they wouldn't be in space-time, and there'd be some sort of interactions that would be not spatio-temporal among the electrons. And then it would be very hard to get, I'm just using electrons because that was the known elementary particle of the day. And then it would be very difficult to recover the space-time from that kind of a framework.
Yeah.
And I think that's the difficulty that he's pointing to.
I agree.
Can I just make, I haven't looked at this, and it seems like there is a kind of, I don't know what to make of it. There's one way of reading it. It seems the way Smolin wanted to read this quote from the first slide had to do with the renunciation of a continuum in favor, presumably, of something discrete.
Einstein could certainly understand.
And if that's all it was,
yeah,
then you can, that something discrete can coarse grain into something that's approximately a continuum and so on is true. I can't imagine Einstein would say, I don't know how that would work.
Exactly.
So if that's all it is, and furthermore, what he means by you say you don't describe it geometrically, you can describe a discrete space-time or a discrete structure geometrically in any norm. I have a whole book about it. Anyway, yeah. In a common geometrical language. So the renunciation of continuum for discreteness, I don't understand how that could be what Einstein had in mind given what he wrote here. He must have something much more radical in mind or he wouldn't have written that.
Raphael, do you agree with that?
I don't think that's in. Yeah, I don't think it's in conflict with what I said.
No, I don't think it is either. The reason I'm asking you is because I'm no expert on this at all, and you are.
Yeah, I think
what Tim said is totally compelling.
I think what it says here is I cannot imagine the axiomatic framework. He's not saying I can't imagine how you could coarse-grain the more fundamental structure to get a space-time. But I think what he's just trying to say is he doesn't understand how to set up the theory. And indeed, I agree with what Tim was suggesting. I think from context that what he had in mind was something more than just a discrete space-time. I think it's something more along the lines of what I just said before. Some collection of particles interacting by an an interaction that's direct of some sort, not spatio-temporal in nature. And space-time comes out as some approximation. That's much harder to understand how that would take place.
And with a description at that level, it would be hard for me to decide whether or not I would find it satisfactory. I mean, because the devil's going to be in the details there. Antonio told us yesterday indicated yesterday that one could have, or attempt to have, a Bohmian theory based on a space-time which was not a continuum, in which the continuum could be emergent. And that's a very natural idea. And that's an idea which is relevant to this list that I'm going to give you here of different levels of abstraction or concreteness that you might have in your ontology. So the most acceptable situation is to have a decoration, as I said before, a decoration of something like that is a quasi-familiar space-time. And by quasi-familiar, I mean it doesn't have to be the familiar space-time or even a continuum. Something like Antonio mentioned could be perfectly adequate depending on how things go. So that's what I mean by quasi-familiar space-time. That would I consider to be a perfectly reasonable kind of ontology to see what comes from that for the formulation of fundamental physical theories. And in that space-time, of course, there ought to be some stuff. If it's empty space-time, we don't exist. Has anybody proposed we could just be deformations of space-time itself?
Yeah, many people.
Okay, so I take it back what I just said. There doesn't have to be anything beyond space-time itself. That's also a possibility. I wouldn't.
Well, even going back.
He talks about it.
Going back to Clifford, in fact, in the.
Okay, so one has to take all of these statements with several grains of salt, because as you can see, as soon as you make a statement, you have to qualify it. Now, second possibility here is a decoration of a very, like David talked about, a decoration of a very high-dimensional space-time regarded as the fundamental space. I consider that very different, and my own opinion is I don't find the way that would work to be adequate. But Tim, there was a long discussion on Monday between Tim and David about this possibility, and I'm not going to return to that further here. Different level entirely, you could have a decoration of, well, no, not a different level entirely. A decoration of a completely abstract space. I'm not so sure that's so different from what David said, because in the way that space, this David space, the high-dimensional space is used, maybe it wouldn't be that different if it were a completely abstract space. Maybe the same kind of functional analysis he gave could be carried out, even in a much more abstract setting, when the space doesn't look merely like a high-dimensional Euclidean space or anything like that. Now we come to a really problematical situation. You have no decoration at all, but it's on space-time. So you're happy, you've got something on space-time, but you don't have anything like that you can understand as a serious decoration of space-time. By that I mean, suppose you have operators on a Hilbert space of wave functions on configuration space. If you've got wave functions on configuration space and you think of the configurations as configurations of things in physical space, then you're talking about a theory where at least there's a suggestion of something on physical space built into the theory. And then you've got the operators which are suggestive of properties, but the operators are at a level of abstraction such that it's not at all clear how they correspond to any distribution of structure on space-time. And then, of course, we have the possibility that you have no decoration and no space-time. For example, abstract operators or more general non-commutative objects, no space-time at all. Hard to see how that's going to go. Now, and maybe I'm coming to the end, I think we do need to finish here. I want to talk about some commonalities in many of the talks. Commonalities among Bohmian mechanics, what Pierre described, what Jörg described, what Fay described, what Raphael described. First, the first commonality, all of these theories involve decorations of space-time or histories. This is an extremely important common core to these theories. As James mentioned yesterday, at least in this commonality in connection with Bohmian mechanics and consistent histories. But I think more or less all the quantum theories about observers here were such theories, as I would say they almost would inevitably have to be. And one point I would like to make about such theories is that they are, or they could be said to be, using the bad language that Bell didn't like and many of us don't like, hidden variables theories, because they do involve what are, in a certain sense, hidden variables. That is, additional variables, additional ontology. Maybe not quite additional if you don't have the wave function at all, but ontology beyond the wave function. They all involve that. And since they all involve that, none of these theories have a measurement problem. Because you have a measurement problem when all you have is the quantum state, and the quantum state is superposed over different possibilities. That's not a problem at all in any of these theories, because these theories are not primarily about the quantum state. They're about stuff happening in the world, and the cat is either dead or alive, and these theories give you probabilities for that. There is no measurement problem. Do you agree, Jörg? So,
what is the ontology in Hohenberg's talk?
I will get to it. Yeah, it's not, at this point it should not, maybe not be so clear. I'll get to that. I think Jörg provided the ontology for Pierre's talk.
Noticed or agree.
What?
Either of them noticed or agree with you.
No, I'll explain what I mean. So let me talk about three different kinds of possible ontologies, although I'm not so sure about all of them. There's what people would call a classical ontology, which I don't like the word classical there, because for me it just means a coherent ontology almost, and the adjective classical, I don't really know what it conveys. But anyway, that's the ontology you have in Bohmian mechanics, particles with positions, world lines. In GRW, mass density or flashes or spontaneous localization, mass density. Perfectly clear ontology. There's no issue about the ontology there. It's clear what you're talking about. Then we have quantum ontology, which almost by its essence is somewhat obscure as an ontology, and I'll say more about that. I suppose maybe we have presumably we have a quantum ontology in consistent histories, but I have a question mark there because at the end of the day, maybe that may not be the best way to think about it. And then we have a macroscopic ontology, which simply means an ontology describing only on the macroscopic level, like Bohr had. You have observable reality, we take seriously, that's what exists, that better exists. And we don't have in the ontology of the physics anything at a deeper level. Remember how controversial, of course, Boltzmann's idea that there are atoms was, because that was something beyond what was observable. It was a huge controversy. Macroscopic ontology, just limit the ontology to what you can see around you.
But isn't that what's called operationalism?
I would call it operationalism.
Right.
I think that would be maybe a clearer way to say what's going on in operationalism. Now, maybe operationalists would say, no, I don't even have a macroscopic ontology. But then I don't know what the hell they're talking about. Are they talking about mental events? Then why don't they should be doing, say, ecology. So presumably they have a macroscopic ontology. Am I right about that? Now, I want to connect macroscopic ontology with the talks of Pierre and Jörg. And so, that might raise the question whether if what they really have at the end of the day is something like a macroscopic ontology, how can that be regarded as a quantum theory without observers? Because even on the level of the ontology of the theory, you're saying it's fundamentally about the macroscopic, then what's fundamental is macroscopic. That's not a, no, don't, what I'm going to point, what I do want to argue is it's not, appearances to the contrary notwithstanding, what they're talking about should be regarded as a quantum theory without observers, despite the fact that in a certain sense it seems like what they have is a macroscopic ontology, and therefore that it's not. I want to argue that's not a correct conclusion. A bit more about quantum ontology, Hilbert space ontology, as Pierre called it. Here is a statement. It's not a quote, I think, but it's similar to something Pierre said. Properties are associated with subspaces of Hilbert space or with projection operators. Subspaces of Hilbert space are very clear things. Projection operators are very clear things. But what is being conveyed by saying that properties are associated with these things is not at all clear. What I mean by that is this. At a first stab, you could say, what I mean by that is I have a one-to-one correspondence between subspaces of Hilbert space and properties. But then the subspaces of Hilbert space are just provide us with an index set. And any other set which had the same cardinality would do just as well. Now, I seriously doubt that the people who say we have a Hilbert space ontology mean that. But if they don't mean that, it would be good to know exactly what they do mean. If they mean, somehow they must mean that the connection between the properties and the subspaces of Hilbert space must be ontologically significant. And the question is, in what way is that ontologically significant? How am I to understand these properties? Now, the problem is not how am I to understand subspaces of Hilbert space. I know what they are. The problem is not how am I to understand projection operators. I know what they are. I just don't, what's difficult is to understand how such statements are to be understood ontologically. What are you saying when you say these are the properties? What kind of properties do you have in mind? For example, if I said reality, ontology is given by the empty, the ontology for physics is given by the empty set. I know exactly what the empty set is, but I don't know what you're telling me about the world when you say that. I probably would know even less if I said, no, they say ontology for physics. Physical ontology is given not by the empty set, but by the set consisting of the empty set. I know what that means, but I don't really know what's being conveyed. Or suppose someone said, the ontology for physics is very simple. It's just the number 42. Everybody knows what the number 42 is, but you would be puzzled. Now there's nothing wrong with having in your, I mean, you can say, okay, I just have these properties in my theory. But if we had properties of this level of abstraction in the theory, whose connection to something in the real world is so obscure, you couldn't get any predictions from the theory about the real world. But you do. Jörg did, Pierre did. So something else must be going on. Let me come to Fay and Raphael. Reality is given by coevents.
Excuse me, what's NRAO?
Oh, I'm sorry. Thank you, Pierre. Naive realism about operators. That is, saying the reality observables correspond to operators, self-adjoint operators, without providing some clarification of what this could mean. Just being naively realistic about them. Okay. Pierre, Fay and Raphael. Reality is given by coevents, by subsets of the space of history. So in the example from their talk, you had two histories, particle going one way or particle going a different way, path A and path C. And the coevent was the set consisting of A and C. A and C, that was the coevent. And the statement was, that's the reality. Now, a path is a very clear thing. and a set of paths is clear enough. So the path, the set consisting of A and C is a perfectly clear thing. And the statement that the reality corresponds to the set A and C would have has a natural interpretation. It is that what happened was either path A or path C. But that's not what Raphael has in mind at all. So he doesn't have in mind the conventional meaning of statements that reality corresponded to a certain set of possibilities. So then one has to ask, what does he have in mind? I mean, again, the abstract notion of a certain set is a perfectly clear thing, but how it connects to reality is totally obscure, and so it's hard to see how any conclusions about what happens in a lab is going to follow from such a description. And yet, for Raphael, those conclusions do really follow. How does that come about? That's what I want to touch upon. And here's basically how it goes, both for all of it, for Pierre, for Jörg, at least my understanding of it, Pierre, Raphael, and Fay. At the end of the day, the reason we get from those theories statements about what happens at the real world is because, at least at the macroscopic level, the projections, the descriptions of the states of the projection operators, the projections, the descriptions of the co-events are taken at face value. The co-event corresponding to this table being here is understood as saying there's a table here. A way to understand that is to say, at least we have in this theory at least a macroscopic ontology, which is to be understood in the usual way. But these theories provide precise formulations, as pretty precise formulations of exactly what kind of things constitute an adequate, what should be taken as the ontology of the theory. What was the name you called for this? Minimal, what was those things?
Primitive co-event?
Yeah, the primitive, so one could say one has you do a lot of work, presumably, getting your hands on the notion of primitive co-events. That work could be regarded as then providing an adequate ontology. The statements about some of these things could be understood, and if this concludes sort of macroscopic descriptions, which are taken at face value, you have perfectly clear predictions of the theory. If, in fact, on a more microscopic level, it's sort of obscure what these things mean, you could just say, okay, it's not, we don't have a precise understanding of what's going on, of the nature of this ontology at the microscopic level, but what we definitely have in the theory is macro variables that behave as predicted, with probabilities as predicted by the theory. Now, so that's what I mean here by classical macro, quantum micro. We could have theories in which, on sort of something like the macro level, we have something very much like a classical ontology, which somehow blends somehow with a more obscure kind of ontology at the micro level. But as long as the macro level ontology is something we understand in Bohr's terms, we get predictions from that theory. Now, Pierre ended his talk by talking about the physical, I think you called it the physical incompleteness of the scheme he had told us about up to a certain point, and talked about the need for, I don't know if I remember exactly what you said, the need for, was it internal selection or was it some other phrase you used?
The selection of a physical framework.
But you have
and
two
it can be
kinds.
done either internally or externally, but internally or externally are just methodological. The important thing is to select a physical framework.
Fine. Now, I want to focus on internal selection because I consider that the better way, but I would consider that the better way. I could regard what Jörg did as providing the means of internal selection. How did he do that? Because he spent most of the mathematical effort was in Jörg's talk was to arrive at what he called, and these words suggested it should be regarded as important for his analysis and his formulation, what he regarded as the ontology of his theory, which he said was a triple: state omega, something which is kind of, I leave out there because I kind of think it's kind of odd to put it in the ontology, the dynamics, but I don't want to quibble about that. And then, and I don't remember the notation you use, so I'm writing C omega. That C stands for center and commuting or whatever. That's what you arrived at the ontology of the theory. And the nature of this thing that you arrived at is such that you can, the usual probability formulas applied to sequences of events from this ontology are not problematical. So you can say that what is in the ontology of theory, well, you have in this theory an ontology with a probability rule for the events which describe the decoration of space-time corresponding to this ontology. And since this selection rule defining the ontology was not a rule which was defined by referring to the notion of macroscopic or anything like that, but in terms of simply internal properties of the structure at hand, it is a quantum theory without observers. Now, I think that's pretty much all I want to say about on a substantive level. So I want to end with a long quotation which expresses well, describes well how I sort of feel when I hear of proposals about, well, in foundations of quantum mechanics, and I guess what's relevant now is proposals of an ontology of an obscure character where I'm just at a loss, like the reality is the number 42. Those proposals bring to mind the following statement of philosopher David Stove. He has this paper in which he talks about the ways our thinking can go wrong, and I find it a very amusing paper. And here's a small selection, a small piece from his paper. Here he says, "Here then are examples of 40 different ways in which thought can go irretrievably wrong, of which we can identify only the first two." We can identify only the first two means it's only in the first two we have a clear idea of what's going wrong. And all of these ways, there's definitely something going wrong, but he says it would take many books to try to analyze, classify the different ways things are going wrong in these statements. So I begin. Between 1960 and 1970, there were 3 U.S. presidents named Johnson. 2. Between 1960 and 1970, there were 3 U.S. presidents named Johnson, and it is not the case that between 1960 and 1970, there were 3 U.S. presidents named Johnson. 3. God is 3 persons in one substance, and one of these persons is Jesus, which is the Lamb that was slain even from the foundations of the world. 4. 3 lies between 2 and 4 only by a particular act of the divine will. 5. 3 lies between 2 and 4 by a moral and spiritual necessity inherent in the nature of numbers. 6. 3 lies between 2 and 4 by a natural and physical necessity inherent in the nature of numbers. 7. 3 lies between 2 and 4 only by a convention which mathematicians have adopted. 8. There is an integer between 2 and 4, but it is not 3, and its true name and nature are not to be revealed. There is no number 3. 3 is the only number. 3 is the highest number. 3 is a large number. 3 is a lucky number. The sum of 3 and 2 is a little greater than 8. 3 is a real object, all right. You are not thinking of nothing when you think of 3. Okay, well, let me skip to the last thing. It may be, though I don't really believe in modalities, that in some other galaxies the sum of 3 and 2 is not 5. Or indeed is neither 5 nor not 5. Then he says, don't laugh. They laughed at Christopher Columbus, you know, and at Copernicus. And even the logical law of excluded middle is being questioned nowadays by some of the sharper young physicists. Thank you for your attention.